in the previous lecture we have seen lot of miscellaneous examples as application of definite integrals. We will continue the same in this lecture also, which will help you in solving complicated problems. Before we start solving certain problems, let us take one concept which is still left and let us learn that. Consider a function f(x) which is continuous on closed interval a b, and for simplicity we can take that f(x) is positive, but the result that I am going to discuss can be extended very easily for any function which is continuous but it may not be positive. So let us draw the curve. This is x equals to b, this is x equals to a, this is y equals to 0, and this is y equals to f(x). So you have this area represented by the integral a to b f(x) dx. You know that if a function is continuous, it attains its bound over the interval. So you can see from this plot that this is the maximum value of the function, and say this is attained at some point x equals to c, and say this is the minimum value of the function which is attained at some point x equals to d. Though we do not need these points, but still I have just written, and say this height is small m, this height is small m, and this height is capital M. You know that this is the green shaded region is the actual area, this is the actual area, and we want to find out a bound of this for the given function. So from this plot you can see that actual area is always greater than this area which I have shaded with, actual area is always greater than this area shaded by black color. And what is the area of this rectangle? That is very easy to see, that the height of this rectangle is small m, and width of the rectangle is b minus a. So the area of the small rectangle will be m into b minus a. Now let us draw this figure again, because it is getting very complicated to understand from this. So something like this, you have this is b, this is a. So this green shaded region is the actual area. So you can see from the figure that actual area A will always be less than area of the rectangle shaded by red color. So actual area will be always less than area of the rectangle shaded by red color. So how to compute this area of the rectangle shaded by red color? So this length is b minus a and this length is capital M. So this area will be always bounded above by and bounded below by this quantity, where M is the maximum value of the function attained in the interval a b, and small m is the minimum value of the function in the interval a comma b. Let us see one example how to get these bounds of the definite integral a to b f x dx. We have done it for continuous function, but you can very easily extend it to this logic for any function which changes its sign. So let us take some example and see how to find out the bound of the definite integral. So example is say 0 to 2 e to the power minus x dx. So this is x, this is y axis, then e power minus x will be this curve. Say this is x equals to 0, this is x equals to 2. So actual area is this. To find out the bounds, let us draw the rectangle. So because function value is taking maximum value at 0, so this will be always lesser than. So what is the height of this? This height is governed by function value at 0, function e to the power minus x, so this height is 1 and this width is 2. So upper bound of this area will be 2. For lower bound we have to draw this rectangle, and since the function is decreasing throughout, so lower bound will be given by area of this rectangle, which is at x equals to 2 function value, that is e power minus 2. So this height is e power minus 2. So area of this rectangle shaded by black color is 2 into e to the power minus 2. So you can see that how this result helps you in finding out upper and lower bounds of any integral. Here m is the maximum value of the function and m is the minimum value of the function. We have assumed f to be continuous on the closed interval a b. Let us finish this discussion and let us move ahead and solve some more miscellaneous exercises on definite integrals. In the sequence, let us consider one example on definite integral given as evaluate minus half to half log 1 plus x upon 1 minus x dx. So let us write the integral as it seems very complicated because we have very heavy functions here, greatest integer function, logarithmic function whose input argument is 1 plus x upon 1 minus x, but you see it is of the form minus half to half, which is which can be related with even and odd functions. So if you see log 1 plus x upon log 1 minus x, if you assume that it is hx, so h of minus x will be log of 1 minus x upon 1 plus x, which you can write as minus of log of 1 plus x by 1 minus x. So this is equal to minus of hx, which is, so this integrand is an odd function of x and interval is minus half to half, therefore the value will be 0 by using the property of definite integrals. So your final integral is minus half to half greatest integer function x dx. So the greatest integer function takes value 0 between, so this is the plot for greatest integer function from 0 to 1, and then from minus half to 0, that is from minus 1 to 1 actually it takes value minus 1. So this will be minus half to 0, we have to break it because function is taking different values in different intervals. We get minus 1 to dx plus 0 to half, it is taking value 0, so we get 0. So minus x minus half to 0, which gives you minus 0, it will be 0, then minus of this will be plus, and then again one more minus, so you have minus half. That is the final answer. So you can see that how for very complicated definite integrals, if you use properties, it becomes much simpler. Let us take another example in this sequence. Evaluate minus pi to pi cos square x dx by 1 plus a to the power x is positive. So if x is, so what should we do? Because if we try to apply formula of even and odd function, it will not work, because cos square x is even function, but this is this does not satisfy 1 plus a to the power x either property, so this is not applicable. So what we do, we first replace x by minus t and see what happens. If x is minus t, then dx is minus dt, and I will be at minus pi, it will be pi, and at pi it will be minus pi. So this is the new limits once you change the variable, and you get cos square minus t dt with a minus sign, dx is minus dt, so minus dt, x is minus c, to cos square minus t plus a to the power minus t. So therefore I is equal to, since you have a negative sign here, you can change the limits, so you get a positive sign, so you get minus pi to pi. This minus sign will be ignored as soon as you change the limits, interchange the limits, and you get cos of minus x is cos x, so you get dt by 1 plus a to the power minus t. Since t is dummy variable, we can write, and let us multiply by e power t on in numerator and denominator, so you get minus pi to pi, and change the variable t to x because it is dummy, so I can write it like this. Now if you add equation 1 and 2, if you add equation 1 and 2, you get 2I is equal to minus pi to pi by a to the power x dx. So this was common, so you get 1 plus a to the power x in the numerator also, so it gets cancelled, and you can see that you got a very simple integration. Now using the, because cos x is even function, you can write 0 twice of 0 to pi, and cos square x you can expand as, by using trigonometric properties of cos x, you can write dx. So value of this will be pi, because this you get here x, that gives you pi, and cos 2x will be sin 2x by 2, and the value of that will be 0 at 0 and pi. Therefore finally you get pi over here. So, I is equal to pi by 2 is the answer. Let us take another example. Compute so you remember this property, a to b fx dx is equal to a to b f a plus b minus x dx. So this you can write immediately as pi by 6 to pi by 3 dx by 1 plus pi by 3 plus pi by 6, this is 60, this is 30. So you will get pi by 2 a plus this a plus b is pi by 2, so pi by 2 minus x. So I is therefore immediately equal to pi by 6 to pi by 3 dx by 1 plus under root cot x, which we can write as under root tan x by 1 plus under root tan x dx. Now if okay, so let me do one thing, let me just add and subtract here. So you get I equals to pi, this is pi by 6 to pi by 3 1 minus, so this is, this we can break it into two parts. So one integral like this, then another one pi by 6 to pi by 3 1 by 1 plus under root tan x dx. This is again I. So you get 2I equals to, value of this integral is pi by 3 minus pi by 6. So therefore I is pi by 12. Let us take another example. Evaluate 0 to pi by 4 log 1 plus tan x dx. So apply this formula. This will be so this is equal to one plus tan pi by 4 minus x dx. This is equal to, this is 0 to pi by 4, 0 to pi by 4 log of 1 plus tan a minus b is tan a minus tan b upon 1 plus tan a tan b. So therefore we get one plus 1 minus tan x upon 1 plus tan x dx, which is equal to 0 to pi by 4 log of, if you take LCM and add it, you get 2 by 1 plus tan x dx. So this is your I, and earlier I was 0 to pi by 4 log of 1 plus tan x dx. Now if you sum both 1 and say this is 2, this was your earlier equation 1. So, if you sum 1 and 2, you get twice of I is equal to 0 to pi by 4 log of 2 upon 1 plus tan x d plus log of 1 plus tan x dx. So, you get 2I equals to 0 to pi by 4 log of 2 by 1 plus tan x into 1 plus tan x dx. This is equal to 0 to pi by 4 log of 2 dx, which is equal to log 2 to pi by 4. 2I is log 2 into pi by 4, therefore I is pi by 8 log 2. Let us take another example. So, find out the value of I, compute I. So, let us just write it in expanded form. So, you get minus pi to pi 2x sin x upon 1 plus cos square x dx. 2x by 1 plus cos square x, say this is fx and say this is gx. So, fx, that is 2x by 1 plus cos square x, is an odd function. This is equal to minus of fx. Therefore, by using property of definite integrals for odd functions, this will be 0, as we know that if fx is odd, then value of the integral is 0 if fx is odd. So, this is odd. Finally, you arrive at this integral. So, your I is minus pi to pi 2x sin x by 1 plus cos square x dx. Now, this, as we said, this is say gx. Gx is an even function, because if you put minus x over here, you get 2 minus x sine of minus x by 1 plus cos square minus x. So, you get 2x sin x by 1 plus cos square x, which is your gx. Therefore, I will be equal to 0 to twice of 0 to pi 2x sin x dx by 1 plus cos square x. So, we are using this property that this can be written as gx dx, this can be written as twice of 0 to a gx dx. Now, again what to do? So, we apply this property that 0 to a fx dx is 0 to a f of a minus x dx. So this is equal to 0 to pi 2 pi minus x sine pi minus x dx upon 1 plus cos square pi minus x. We get I as 4 0 to pi minus x, sin pi minus x is sin x and cos pi minus x is minus cos x, but since it is a square, so you get again cos square x. Now if this is 1, this is 2, by adding 1 and 2 you will see that this term will be cancelled. So by adding 1 and 2 you get twice of I is equal to 4 times 0 to pi sin x dx by 1 plus cos square x. Now let cos x is t, so minus sin x dx is dt. So I is equal to, if I cancel it, so I is 2 pi, at cos 0 it is 1, cos pi is minus 1, sin x dx is minus dt, so you get minus dt, 1 plus t square. So this is equal to 2 pi, if because there is a minus sign you can interchange the limit, so you get minus 1 to 1 dt by 1 plus t square. So I is therefore 2 pi tan inverse t minus 1 to 1 2 pi pi by 4 minus pi by 4. So you get I equals to 2 pi by 2. So you get your final answer for this integral as pi square. Let us take one more example. Evaluate 0 to pi x dx 1 plus cos alpha sin x, where alpha is given to be lying between 0 and pi. So let this integral is I. So I you can write by using the property that 0 to a fx dx is same as 0 to a f a minus x dx. You can write 0 to pi, x is replaced by pi minus x, 1 plus cos alpha sin pi minus x. So again sin pi minus x is sin x, so numerator of say 1 and 2 both will be same. So if you add, so you get 2i on this side and this side will be pi dx upon 1 plus cos alpha sin x, which we can write as pi 0 to pi dx by sin square x by 2 plus cos square x by 2. 1 you can replace by sin square x by 2 plus cos square x by 2 plus let me write it here, cos alpha you can expand it to 2 sin x by 2 cos x by 2. So therefore 2i is equal to pi 0 to pi. If you divide by cos square x throughout in the numerator and denominator, so you get sec square x by 2 dx by tan square x by 2 plus 1 plus 2 tan x by 2 cos alpha. So this we can write as I is equal to pi by 2 0 to pi. Let me take sec is not sec. Let me take tan x by 2 as t. So you get sec square x by 2 dx is equal to 2 dt, and the limit tan 0 will be 0. So t, the limit will be 0 at pi, it will be, so tan, you get tan pi by 2 which is infinity, so limit will be 0 to infinity. So you get sec square x by 2 dx is 2 dt, 2 dt plus t square plus 1 plus 2t cos alpha. This we can write as t plus cos alpha whole square. So we have to add cos square alpha and we have to subtract cos square alpha. So we get t, this together will give you t plus cos alpha whole square, and 1 minus cos square alpha is sin square alpha. So this is of the kind 1 upon a square plus x square. So this value of this integral you can write as 1 by a tan inverse t plus cos alpha by sin alpha, limit from 0 to infinity. So finally you arrived at I is equal to pi by sin alpha. Sin alpha is constant, so you can take it out. We get tan inverse infinity minus tan inverse cot alpha. So because the alpha lies between 0 and pi, it is not 0 and pi, so sin alpha is non-zero, so it is defined. This will give you pi by 2 minus, this you can write as tan pi by 2 minus alpha, so you get again, so your value of the integration is pi alpha by sin alpha. So I is, final value of the integration is pi alpha by sin alpha. Alpha is given to be between 0 and pi. This completes the solution of this problem. Let us take one more exercise on definite integrals. 0 to pi by 2 x sin x cos x dx by cos power 4x plus sin power 4x. So use the property 0 to a fx dx is same as 0 to a f a minus x dx. So this will give you 0 to pi by 2 minus x sin pi by 2 minus x cos pi by 2 minus x dx by cos power 4 pi by 2 minus x plus sin power 4 pi by 2 minus x. This is equal to 0 to pi by 2 minus x, sin pi by 2 minus x is cos x, cos pi by 2 minus x is sin x by cos pi by 2 minus x is sin x, so we get sin power 4x, sin pi by 2 minus x is cos x, so we get cos power 4x. So this is your I. If this is 1 and this is 2, So, if you add 1 and 2, you get this term will get cancelled with this term. So, you get I, you get as 2I. If you add 1 and 2, you get 2I equals to 0 to pi by 2 pi by 2 sin x cos x by cos power 4x plus sin power 4x dx. So, I is pi by 4, 0 to pi by 2 sin x cos x by cos power 4x plus sin power 4x dx. Now, divide by cos power 4x, you get dx. So, I is equal to pi by 4, 0 to pi by 2 tan x and sec square x dx 1 plus tan power 4x. 1 cos x will get cancelled from here. So, you get 3, and then 1 is adjusted with sin x, so you get tan x, and the 1 by cos square x is giving you sec square x. So, therefore, I is equal to pi by 4 tan square x. Let us take that tan square x is t, so that this will be your dt. So, you get 2 tan x sec square x dx is equal to dt. So, tan x sec square x dx is 1 by 2 dt. Tan 0 is 0, tan pi by 2 is infinity. So, limits will be t limits will be from 0 to infinity. Tan x sec square x dx is dt by 2. This is equal to dt by 2. So, you get dt by 2 by 1 plus t square. So, I is pi by 8 0 to infinity dt by 1 plus t square. So, this is pi by 8 tan inverse t 0 to infinity. So, I is pi by 8 tan inverse infinity minus tan inverse 0. Tan inverse 0 is 0, and tan inverse infinity is pi by 2. So, you get pi square by 16. So, your answer is pi square by 16. Let us take one more example. Evaluate 0 to pi by 4 sin x plus cos x dx by 9 plus 16 sin 2x. So, this we can write as sin x plus cos x by 25 minus 16 plus 16 sin 2x dx. So, this can be written as (25 minus 16) 1 minus sin 2x dx. This we can write as 0 to pi by 4 sin x plus cos x dx 25 minus 16. 1 you can replace by sin square x plus cos square x, minus 2 sin x cos x. So we can write this as (25 minus 16) sin x minus cos x whole square. Now let sin x minus cos x is t, so cos x plus sin x dx is dt. This will change the limits. So sin 0 is 0, cos 0 is minus 1, and sin pi by 4, cos pi by 4, both values are same, so it will get 0. So x pi by 4 t is 0, x 0 t is minus 1. Hence you have these limits minus 1 to 0, and you get this as dt. So the value of the integral is dt by 25 minus 16 t square. This is equal to minus 1 to 0 1 by 16 dt by 5 by 4 whole square minus t square. Now using this formula dx by a square minus x square, you can write this value as 1 by 2a log of mod a plus x by mod a minus x. So therefore this is equal to 1 by 16. 1 by 2a is 5 by 4 log of 5 by 4 plus t on 5 by 4 minus t minus 1 to 0. So you get 1 by 40 log of 5 by, so at 0 you will get 5 by 4 by 5 by 4, so log 1 minus log, you will get minus 1 will give you 1 by 4, and this will give you 9 by 4. So this is equal to 1 by 40. Log 1 is 0, then you get minus 1 log 1 by 9, which is, so this you can write as 9 to the power minus 1, and this minus 1 will get cancelled by using property of log. So you get 1 by 40 log 9, which you can write as log 3 square log 3. So 1 by 20 log 3 is the final answer. Let us take one more example on area. Sketch the region bounded between y equals to x square and y equals to 2 by 1 plus x square. Find out its area. So let us first plot y equals to 2 by 1 plus x square. Though we have plotted it earlier, but let us plot it in more detail. So compute y dash, you get, and then differentiation of this will give you 2. So you get minus 4x by 1 plus x square whole square. So, if x is positive, y dash is negative. If x is negative, y dash is positive. And this is true for all x. This is true for all x. So, when x is positive, y dash is less than 0. So, this is decreasing. When x is negative, y dash is positive. So, this curve is increasing. At 0, the function value is 2 upon 1 plus 0, so 2. So, how this, and at y prime at 0 is 0, which is clear from here. So, y prime, if you put 0, you will get 0 from here, right. So, let us plot this. So, at 0, the function value is 2, is 0 comma 2. At 0, the tangent is parallel to x axis. So, the curve is like this. For positive x axis, it is decreasing, and for negative x axis, it is increasing. So, this is the curve y equals to 2 upon 1 plus x square. Now, let us plot y equals to x square and y equals to 2 upon 1 plus x square. So, let us plot both curve in the same plane. So, your parabola is y equals to x square is vertex 0 0, axis y axis, and the other curve is represented by this. This is your y equals to 2 upon 1 plus x square. This point is 0 comma 2, 0 0. We need to find out these point of intersection. So, the area that is required is shaded by red color. We want to find out area bounded between both the curves. So, we need to find out the point of intersection of both the curves. So, solve both the curves, you get let us do it because it will be lengthy. So, you put x square as y. So, you get y equals to 2 upon 1 plus y. So, you get y square plus y minus 2, this is 0. So, y is minus 2 and 1, y is minus 2 and 1. So, since y is always positive, so minus 2 is to be ignored. So, y is 1, is y equals to 1. So, corresponding values of x, so if you put y equals to 1, so corresponding values of x are x equals to plus minus 1. So, this is your x equals to minus 1 and this is your x equals to plus 1. So, your area will be minus 1 to 1 because you have got, let me draw it again because otherwise how to tell you the limits. So, you have the situation, this is your one curve, the other curve is this, and this is minus 1, this is plus 1. So, this is your required area, this is elementary area, this whose width is dx, and this is 2 by 1 plus x square, this is x square. So, you get 2 by 1 plus x square minus x square dx is the elementary area. So, value of the required area is So required area is red shaded region. So this is equal to 2 minus 1 to 1 dx by 1 plus x square minus 1 to 1 x square dx. 2 tan inverse x minus 1 to 1 minus x cube by 3 minus 1 to 1 2, this is pi by 4 minus pi by 4 minus 1 by 3 1 minus 1. So your final value will be, this is pi by 2, so pi, and this is 1 minus 1 minus, this is 2, so you get pi minus 2 by 3. So this is the final answer. Let us take one more example. Sketch the region sketch the curves and identify the region bounded by x is equal to half, x equals to 2, y equals to log x, and y equals to 2 to the power x. So if you plot the region, log x is drawn like this. This is x equals to 1, and then 2 to the power x, at 0 it is 1, and then when x increases its value increases, so it goes like that. So say this is x equals to 2, x is equal to half is somewhere here, so this is your half. So this curve is 2 to the power x, this is log x, this is x equals to half, say this is x equals to 2. So your region of integration is this. So to solve this, again you need to define elementary area. So elementary area is fx, this is your fx, this is your gx, so fx minus gx, try to recall the formula, into dx, so 2 to the power x minus log x into dx, and limits of integration will be from minimum to maximum value of x, that is from x equals to half to x equals to 2. So value of the integration will be 2 to the power x by log 2 minus value of log x will be x log x minus x, limit goes from half to 2. So value is therefore at 2 you will get 2 square by log 2 minus 2 log 2 minus plus 2 minus, at half you will get root 2 by log 2 minus half log half minus plus half. So you get 4 minus root 2 by log 2 by combining these two terms, then 2 minus half will be 3 by 2 by combining these two terms, then these two terms together will give you this. If you take this, you can write this as plus half log 2. So, therefore, you get minus, this is okay, you have a minus sign here. So, you have minus sign here, you get plus, again you get a minus. So, you get 5 by 2 log 2. So, this is your final answer. So, see this is a minus sign. So, this minus minus will be plus, but because 1 by 2 is there, so that will again be minus. So, this term and this term will be clubbed together. So, 2 plus 1 by 2 is 5 by 2. So, hence this is the final answer. With this we stop. Thanks for listening.